Hello! What I've got for you today is a video on two-dimensional Coulomb forces. So this is the force between two charged objects. And we're going to do it in two dimensions, so instead of everything being on one line, we're going to actually have things in a square. Well, triangle, I guess. So the situation we have three charged particles. And we have a -4 nanocoulomb particle, and a +8 nanocoulomb, and a -6 nanocoulomb. We are given that the distance between the particles, this is 6 centimeters, and this one is 7 centimeters. And our first question, what is the total force on the 6 nanocoulomb particle? So my question is, what is the net force or total force on the -6? Now if you go back to forces, you just think about what forces are from first semester. Well, okay, so to get the net force, the total force, we just figure out what all the individual forces are and add them up. That's as easy as it is, but they are vectors. Remember that force is a vector. It has direction as well as size. So we have to take into account the direction of the forces on this 6 when we're doing this. Now, how many forces is it going to feel? And again, one of the tricky points is I want what it feels, not what it does. What does this feel? If you are the -6, that's what you should put in your brain. If you are the -6, what do you feel? So I'm a -6, and there's a negative here. Well, we're both negative. That's a repel. So I'm going to have a force going down, repelling me. So there's the force of the 4 acting on the -6. It's pushing it away. Again, I'm the negative. Here's a positive. It's opposites, attraction. So what does the 6 feel? It feels a pull up to that 8. So we have two forces acting on this -6. And we need to figure out what they are, how big they are, and then figure out what direction they're in so we can add them as vectors. Once we have added them as vectors, we can get the total force, the net force on that -6. So what do? Well, we are going to use Coulomb's law. This is 2D Coulomb problem. So the force of the 4 on the 6. And the reason I'm ignoring the signs is because the signs here are only telling us direction, if it's an attraction or repulsion. This Coulomb's law, K, Q1, Q2 over R squared, that is only telling me the size of the force. So K, Q1, Q2 over R squared, that's our Coulomb's law. So for this one, the 4 on the 6, K is a constant, 9 times 10 to the 9th. Q1, one of the charges, let's do the 4. So that's 4 nanocoulombs, 4 times 10 to the -9. The other charge, 6 times 10 to the -9, because it's nanocoulombs. And then the distance between those two charges. What's the distance between the 6 and the 4? 7 centimeters. Centimeters. That should make a little warning bell in your head. We need to convert that to meters. So it's 0.07 meters. And don't forget the squared. That's a common mistake. I guess 2 common mistakes. Not to convert to meters and to forget the squared. So don't forget those 2. Meters, squared. If we do this, we get a value of, what do we get? 4.41 times 10 to the -5 newtons. That's the size. Coulomb's law only tells us the size. This is really, if you think about it, it's the absolute value. That's why I ignored the negative signs in here. Because what would a negative mean? Left, down? It doesn't tell us anything. So really, this is just the size. Coulomb's law is the size, the magnitude. We have to look at our picture in order to figure out what the direction is. In this case, it's pretty easy. This is the 4 repelling the 6. So it's 4.41 times 10 to the -5 newtons, straight down. All right, that is the first force. We're going to do the same thing for the second force. The force of the 8 acting on the 6, K, Q1, Q2 over R squared, 9 times 10 to the 9th. And now we have 8 nanocoulombs. times 6 nanocoulombs all over the distance between them. Don't know it. All right, so what do? How do we get the distance between them? Well, I know 2 of the 3 sides of the triangle. So what I typically do is off in the corner of my paper somewhere, I will draw the triangle that I'm dealing with. So this is 6 centimeters, this is 7 centimeters, and I can do Pythagorean theorem. 6 squared plus 7 squared equals this squared. And if I do that, this side is 9.22 centimeters. You could do it in meters too if you wanted. 0.06 squared plus 0.07 squared equals 0.0922 squared. All right, so there we go. But I also want to know the angle. So I'm going to do the inverse tangent of something. I tend to go from the horizontal. I just like going from the horizontal. So if this is my angle, opposite is 7 over 6. Okay, so the inverse tangent of 7 over 6 equals the angle, and that angle ends up being 49 degrees. All right, now I can go back and do this. So what is the distance, r squared, distance between 8 and 6? That is this hypotenuse, 9.22 centimeters, 0.0922. Don't forget the squared. So that's squared on the bottom. Which means, if we do the calculation, the force of the 8 on the 6 ends up being 5.08 times 10 to the minus 5 newtons. And again, the calculation just gives me the size. I have to look at my picture to figure out the direction. And this force is attracting up. The 8 is attracting the 6 up along this direction. Well, this direction is the same as this direction, because that's the same triangle. So I need to describe it somehow using this triangle. And the 6, 7, and 9.22 aren't helpful. Those are the size of the sides. I want the angle. Well, if this angle right here is 49 degrees, then the equivalent angle there is 49 degrees. So I now know that this force acts up and to the right at 49 degrees above the horizontal. So that's step 1. We have figured out the size of the 2 forces and the direction of the 2 forces that the 6 is feeling. So it's feeling a repulsion straight down, a traction up and to the right. And now we're going to add them as vectors. We can't just add them together because they're in totally different directions. They are vectors. And there are a lot of ways to do this. If you have a particular way you like to add vectors, go ahead and do it that way. That's fine. The way that I find makes the most sense for me, I'm actually going to clean this up just a little bit. I use a table where I break up the x and the y components of all of my vectors. So I'm going to get rid of this. We already did that calculation. I want to get myself some more space. Okay. I tend to do an XY table where I break up into the horizontal and vertical components all of my forces. I have 2 forces in this case. I have the force of the 4 acting on the 6 and the force of the 8 acting on the 6. And I'm going to break them up into their components, and then I'm going to total them up, add them together. That'll give me my total horizontal piece and my total vertical piece. And then I'll be almost done. There will be 1 step left after that. All right, so the force of the 4 on the 6. This is the size of it, and it's acting straight down. Well, that one's actually pretty easy then. The horizontal component of something going straight down is nothing. So there is no horizontal component. The x component is 0. The y component, that means, is the entire thing. All of it is in the y direction, so 4.41, but it's downward. So I need to remember to throw a negative in there. And just to save space, I'm going to get rid of all the times 10 to the 5s, because that's a lot of writing, and I don't have a lot of space. So we've done the first one. We have the 4 on the 6. Its horizontal component is nothing. Its vertical component is downward at 4.41. Now I need to figure out the components of the 8 on the 6. All right, the size of it is 5.08 times 10 to the minus 5, and it is acting up and to the right at 49 degrees above horizontal. That means this is going to be its x component, this is going to be its y component, and we can do the same thing we've done with all of our vectors. This is the horizontal piece, it's adjacent to the angle. Adjacent tells me it is the cosine component. So the x component of this vector is going to be 5.08 times the cosine of 49. And now I have to stop and say, is it positive or negative? Well, we're going up and to the right. Up means a positive y, to the right means a positive x. So this is going to be what I end up with for my horizontal component of this vector. Y component is opposite, so that is going to be 5.08 times the sine of 49 degrees. And if I calculate those two, I get a positive 3.33 times 10 to the minus 5. And the x component is positive 3.83. Okay, so what I just did is I broke up this vector into its horizontal and its vertical components. And I kind of did the same thing with this vector, only it was already in one of its components. It is all in one component. So this one was the easy one. I've got everything, now I can add them up. So here are all my x's. I can do that one in my head. Plus 3.33 times 10 to the minus 5. So that is the total force in the x direction. Same thing with y. Negative 4.41, positive 3.83 gives us 58? Yeah, 58. All right. Negative 0.58 times 10 to the minus 5. All right, this means this is the total vertical component of this force. So if I actually wrote these numbers down, this side would be the 3.33 and this would be 3.83. Right, I have my total x and my total y. That's not a vector yet. Those are vector components. I want the total force, the net force acting on the 6, which means I need the size and direction. One last step. So now I'm going to do kind of the reverse of what I just did here. Here I went from a vector into components. Now I have components, and I'm going to slap them together into a vector. I have an x component, positive. So we're going to the right at 3.33 times 10 to the minus 5 newtons. I have a y component that's negative, so I'm going down at 0.58. To the right and down. All right. And now what I'm going to do is figure out what this is. This vector here is my net force. So how do I figure it out? Well, I know 2 of the 3 sides. I can use the Pythagorean theorem to get my net force, the size of it, the magnitude of it, just like I did right here. So 3.33 squared plus 0.58 squared is going to be 3.38 times 10 to the minus 5 newtons. That's the size. What is the direction? I need to know this angle. Just like here, I'm going to do the inverse tangent of opposite, 0.58, over adjacent, 3.33. That's going to give me my angle. If you calculate that, you get 9.9 degrees. Okay, don't stop here. I want the answer in a nice, clean format, and I have no room. So the final answer for what is the net force on the minus 6. So the net force on the minus 6 nanocoulomb charge is 3.4 times 10 to the minus 5 newtons at, and now here you could do multiple ways of describing it. You could say 10 degrees south of east. So we go to the east and 10 degrees south of it. You could say at minus 10 degrees, that's using 0, 90, 180, 270. Or you could say positive 350 degrees. All of those would be reasonable ways to describe the direction. If you just gave me 10 degrees, I would probably think that's starting at 0 and going up 10. That would be up and to the right. That's not right. That's not correct. So make sure you give me some direction to tell me what that 10 degrees there, what that really represents. All right, so have we answered the question? Yes, we have answered the question. Is it reasonable? This is a little bit harder to answer with these kind of problems because we don't have a good sense of what is a 4 nanocoulomb charge, what is a 6 nanocoulomb charge. All we can really do is say, well, if this force was 4.5 and this force was 5, a force of 3.4, at least it's in the right realm. And then we could ask about the direction. We had one thing going down and one thing going to the right. We know the total force has to go to the right because there's nothing to the left. So it has to go to the right. Yep. And then up or down, well, the down was that big. The up was, yeah, not that much bigger. So down and to the right does seem reasonable. So we've answered the question, and as far as we can tell, the answer is reasonable. So that really is a good example of a two-dimensional Coulomb's law problem. Now, what I'm going to do in the next video is I'm going to have the exact same setup, but I'm going to figure out the total force on the +8. And if you want a little extra practice, what you could do is, before you watch that next video, see if you can follow this exact same process and solve for the net force on the +8. Give it a try. And then good job for watching this one.